Okay, let's actually do a little math, because math is a process, and even if we only get through a little bit of stuff, I want you to start thinking about a few little things here. So let's take the function. How about if we take the function? Take this. Take two functions. Let's take the function f of x equals 2x minus 3 on one side. And then over here, we're going to take the function g of x equals x cubed minus 1 over x minus 1. Okay? If I graph these, I would end up with something like, well, tell me you can graph that one. What's that going to look like? What is it? Line. Tell me what are the parameters? Y-intercept? Negative 3. Slope 2. So it looks like that, right? Okay, what about this guy? Well, this is going to end up being equivalent to the parabola x squared plus x. So it's going to look something like this. It's going to look like, well, let's just say something like that. Close enough. Okay. All right, so what do we do with these functions? Well, we could try to evaluate functions, right? Like let's evaluate this first one at 1. What do we get? Yeah, negative 1, don't I? Okay, what's that mean? What's an equivalent way of saying that expression? When I input 1, I get, yeah, so those are just coordinates of a point, right? We evaluate the function, we get a y value. Okay, so that's the point right there, it looks like. Okay. Let's do the same thing over here. Let's take g of 1 equals what? Doesn't work, does it? Okay. When we write that g of x, one thing we should do, and we'll talk more about this, but this is good review. We got to be a little careful. It's implied up here that the domain is all real numbers, isn't it? Right? But not here. What value of x must we exclude from our domain? 1. How come? You're right. Because you can't divide by 0, right? There's two fundamental rules for real numbers. Can't divide by 0. What's the other one? Can't, for real numbers. Can't take an even root of a what? Of a negative number. Yeah. Right, I can't, for example, square root would be the simplest even. I can't take square root of a negative. I can do that, but it's not going to be a real result. It's going to be pure imaginary, right? So we have to exclude 1. What's that mean in terms of our function? Well, it means there's a hiccup, right? Our function has a hole because it's not defined for x equals 1. So at x equals 1, oh shoot, what did I do? I always do crazy stuff up here. So I got to do this. I do that. There's no value for the function. Okay, but I might want to know what value are we close to, right? And one way I do that, the way that we do that in math is by taking a limit. Did you guys talk about limits last year? Didn't talk about limits? Okay. So I could do something like this. I could say, over here, I could say the limit of f of x as x approaches 1 is what? What's that mean? The limit. Here's a way to think about it. A limit is the value that the function approaches as we approach a certain discrete x value, right? One thing I want to say immediately though, and I'll repeat this in different ways about 1 billion times this year, is that you never get there with a limit. X approaches but never gets to 1 in this case, right? That's really important to remember that because that's fundamental to understanding the behavior of a limit. One way to kind of visualize this, and this might seem a little hokey, but it seems to work for people. We always talk about calculus ants, right? So imagine the calculus ant. It's point-like in size, intelligent. It walks along two-dimensional functions. So what we want to know is we want the calculus ant, which can sense its coordinates, by the way, on the xy plane. We want the calculus ant to report back as it gets closer and closer on the function to an x value of 1, what y value does he imagine that, or she, that he or she is approaching, right? That's what a limit means. So as the ant walks along this line and approaches an x value of 1, well, here's the ant walking along the function from either direction, right? What value is the ant approaching? What y value? -1. Prove it. Okay, because that is the value on the function there, isn't it? Right? We can plug it into the function and we get a y value of -1. There's my proof. So that's the value that the ant is approaching, right? Agreed? So the answer is -1. Now there's a shorthand notation for this, right? In calculus, we don't want to use all those words. That's not math, right? We want to condense that into something more efficient. So we would say it this way: the limit of f of x as x approaches +1 is -1. Okay, that's our way of making that statement, right? Agreed? Okay, let's do the same thing over here. That was easy, right? No big deal. So what about over here? We'll just jump right to the shorthand. The limit of my other function, g of x, as x approaches +1 is what? Well, I don't even know if I've drawn the function right. Okay, we don't know the answer, do we? Right? Because we can't, the function is not defined at 1. But the limit exists because how many points are missing from this function? Exactly 1, right? How many points are contained in the function? An infinite number. In fact, how many points are contained within any interval on the function? That's weird, isn't it? But it's true, right? Regardless of what interval you take, there's an infinite number of points on that interval, right? So how are we going to do this one? This is tougher, right? We can't just plug in 1 to figure out what are the coordinates of that 1 point, because that 1 point doesn't exist. So what can we do? We could plug in any of the other numbers. That's one good strategy, right? We could just like pull up a calculator, which I'm going to do. Hopefully this will work. Once again, there's always a little bit of an adventure at the beginning of the year to get these things to work. Okay, this is good practice too. I want you to kind of get used to using your calculator effectively. So how about if we define a function here? We'll go to y equals. We'll define a function, and wasn't it x cubed minus 1?
Yeah.
Divided by the quantity x minus 1, right? We'll just go assume 6, see what that looks like. Yeah, there it is, right? Okay, let's just check, see how smart the calculator is. Let's evaluate the function at certain points. Now, I'll remind you how to do this. This is, you guys know how to do this stuff on a calculator pretty well? So you know about the second calc menu, right? Okay, so we can plug in a value like 2. Oops, that's not what I want to do. I want to go second calc 1 for value. Now I'll plug in 2. And when x is 2, y is 7. There's a shortcut for that. If I'm on the graph, I can just go trace and type in a value. That works too. Like I can go trace -1, enter, That's a little quicker, right? So let's try trace 1, and oh, we don't get a y value. That's the calculator's way of saying tough luck. There is no y value there, right? Okay, but good suggestion was made. Why don't we just try some other values, right? Let's go to the table. So we've got our function in there. Now we can go, let's go ahead and set up this table. It's probably set up fine. Starts at 0. Let's start at 1. And let's make the delta values on the table, let's make the steps like 0.1. How about? So something like that. And now I'm just going to go table. Okay, and I'll back up a little bit. So what's that doing? Can everybody see that okay? So that's just giving, I'm taking values, symmetrical values around 1, and I'm finding the y values. And they ought to be approaching a value, shouldn't they? And isn't that kind of what you were alluding to? Right? That's good strategy, right? But I don't know, what's halfway between 2.7 and 3.31? It looks like it's probably 3, right? What could we do to be a little more certain about it? Meaning, okay, yeah, let's make the intervals smaller, right? So we could do something like, let's go back to our table and let's center it on 1 again, but this time let's go by I'm going to go by 0.01. See what happens there. Yeah, I think we're pretty safe, aren't we? We're pretty safe. Doesn't it seem like it's converging on 3? Okay. Well, hold that thought. Tomorrow we'll pick up with this and kind of start in earnest.